Hi everyone. So there's this old project I made in 2016 where I tried to visualize special relativity, and it basically was me showing this variation of a Minkowski diagram, like this. Now, for whatever reason, for 10 years, basically, I didn't share the source code online, but now I have on GitHub and I want to talk about it. So, before I dive into the actual source code itself, the reason I was inspired to do this 10 years later is because my friend, Io Pasta, also known as Aditya, released his own video for the Summer of Math Exposition 4 about 4D ray tracing and basically visualizing what spacetime looks like when black holes get involved, or just kind of like the distortion that happens, and it's all ray traced, so it's a bit more advanced than mine, which is not ray traced. But it did make me think, like, oh yeah, I remember my project from all those years ago. Let me make it so that more people can play it. So anyway, here's the source code, and if you download it, you should be able to open relativity.pde in processing 4, which is right here. And if you so basically, this is the source code I wrote 10 years ago with some slight tweaks that I added just now, just to make it able to render to a video. So the last thing that I actually simulated in the video was Fiery and Coney slapping each other, and then when they slap, it pushes them away at 80% the speed of light. And right now we're taking Coney's point of view. So I can close this, and you can actually edit the... Oh yeah, it saves the file to your computer folder directory. You can change the paths that they actually make using this code right here. So I is going from 0 to length, which is from the left side of the screen to the right side. And the shape of the paths is basically described by these math functions. So you can see that after 100, which is about a third of the way through, the slap occurs. And I don't know why, but for some reason, all the speeds are multiplied by 1/10. So 80% of the speed of light looks like 0.08. But let's say I wanted Coney to slap out much shorter or slower. So then it's 0.01. So then if you play it again, you'll see that Coney's speed, the slope here is now 1/8 the extremity of Fiery's speed. And that means that when the distortion happens, it'll be much less severe, like that. And I think what's interesting about that is you can toy around with it and see other things. Like maybe you decide, like, what if we did like do a sine wave? I have no idea if this is gonna work because I've not tried this before. And I also think that, like, let's do sine, and then, because it might go above the speed of light, in which case the whole thing will break. But let's make it a little bit slower, like the periodicity of the sine wave will be less severe. So, okay, it's way too... Okay, so that's the thing, it's test and check. You can see there's a very slight sine wave, but it's like so subtle, I don't think this is really what we're going for. Oh, actually, you can see like pretty... Oh, interesting. Okay, so you saw that like the distortion happened instantly, and that's because the derivative of sine right at the beginning is already it's 1. You know, derivative of sine is cosine, so the slope right at the beginning of sine will be 1. So actually, maybe to make this a little more realistic, let's do cosine -1, so that we start at 0 and with a derivative of 0. But let's make it a bit more extreme so that like you can see it better, and make the period a bit faster. So now... Oh, yeah, there we go. Well, it's going up instead of down. It doesn't really matter. But this is just to show how flexible everything is, and you should be able to, you know, put your own curves. And there we go. So you see, like, very smooth. I think it's, you call it both C0 and C1. It's also C2 continuous. I think using a sine wave, it should be C infinity continuous. It doesn't really matter. But basically, like, you can use this to sort of test different things out. And this should basically cover everything. If you want to change the actual images being used, you can see this thing says images folder, and if you actually head to that folder itself, you have multiple options. So these are all the files I made for the actual like visualization itself. So I can't make that any bigger, can I? But like instead of the slap images, which gives you fiery, Coney, and spongy, maybe you want to use the blocky images, which are blocky, eraser, and pen. So if I were to do that right now and change this with blocky images, it'll read from that folder instead. And you can also see there's other stuff here. Oh, I see. Like, people count as 5. And the reason it was divided by 10 earlier is because there's this variable called per square. I just forgot that that existed. So now you can see the visualization has blocky and eraser, and everything else is the same. And you can also tweak the colors of the lines, because that's also described in the thing as well. Also, the light ray shows up as pen, because pen is the... Well, I don't know. I'll have to look into the code itself, or you can figure it out. But you can change the color here, too. So if you wanted to make everyone, like, a bright magenta, you could do that. And I think... I'm trying to think if there's anything else you need to know about. Okay, so, like, okay. let me run this again. Let me make it so you don't have to wait as long before the slap happens. So instead of 100, let's make it 20. And I know this is like magic numbers. Don't really care. Yes. See, now they're magenta, and also the slap happens so it's faster. Okay, so this should be able to get you like everything that you'd want. Wait, hold on. Let me make this small again. Except for certain paths that are like harder to define. For example, in the one where golf ball and tennis ball are orbiting each other. Okay, so yeah, that's happening. That's fun. Here, what's difficult about that is that it's a curve such that when tennis ball switches his frame of reference, golf ball's path now looks the same as it was before he switched it, which means that the input variables, like the input values for this line, are pretty predictable here, but then they kind of get distorted. And the way I did that was actually really roundabout. So what I did was I took on tennis ball's frame of reference, and I had that was easy to code in. It's just like a piecewise function from a linear line to like a exponential or something. I'm not quite sure. And then what I did was I actually like ran the simulation, and then I took like the pixel values for like where you would be if you were like at this location or this location, and I had it printed out. So if I have this variable, see this says should print GB path. If I make it true, what it does is it actually prints out where points lie as the simulation is going. Like you see these numbers here, and using that I would copy that and then paste that back into like some array or something, and then I would run it a second time. Obviously, like that is kind of like not mathematically precise, but it was close enough that like, you know, if you do it with a high enough resolution, it basically looks correct. So I mean, that should only happen for the more advanced simulations, of course, but I thought I would put that out there. The last thing I want to mention is sort of the motivation or the story behind. Oh, first of all, yeah, I did mention Iopasta's channel because I want you guys to go check it out if you're interested in physics, because it's half an hour about the math behind it all, and I think it's very interesting, and there's a lot of cool visualizations. So you can see like there's like a matrix multiplication, but like I just remember there's like the Iopasta's famous warping TV. You know, like you can see this is a Minkowski diagram right here, or Minkowski. I don't quite know how it's pronounced, but there's just a lot of like fun visualizations. So you should really watch it. You know, I think we need more STEM content to be known online. So check it out, Iopasta. I'll put a link in the description. But anyway, I wanted to tell the story of how this came about, because in this video I did mention at some point, like those of you who, okay, so basically down here I said, second, there's this thing called a Minkowski diagram, which my visualizer might actually be very similar to, so oops. I guess that's what I get for not doing any research beforehand. So I wanted to explain some of the backstory. Also, because if you scroll down to the comments section, actually I really want to mention this, because okay, there's a lot of things I want to mention. So Professor EGAD said, whoa, stop. You didn't know about Minkowski diagrams before you made this series? You were so spot on about this stuff that I assumed you were feigning ignorance while you walk us through a few lectures from the final year of a physics degree. I actually have a physics degree, and I'm delighted and informed by your simulation narration. With a bit of tidying up and introducing official vocab, these videos could go on for... Oh, wow. Oh my god, thank you for the best explanation of special relativity I've seen, including those I had at university, to the definitive educational video on the topic. Well, thank you so much. I wanted to like talk about a few things. One is that I remember reading this comment in like 2018, like only a few years after this video came out, and I was like very heartwarmed by the comment, but I was like so nervous about it. Like I was almost intimidated by the fact that someone like who was so well educated was in my comments, that I kind of like ran off and I didn't respond. And this is actually part of the reason why I kind of wish YouTube private messages still existed, because there's no way for me to reach out to these people besides trying to find them on some other platform like Twitter or email or Discord. And also, is this back when Google Plus existed because of the plus signs? Anyway, what I wanted to mention is like, how did this happen and what was my physics education? So I guess for context, like I did take AP physics in high school a few years earlier, which was like 2013, but it did not cover special relativity. It basically just covered like Newtonian mechanics. And what happened was, I remember in Christmas of 2015, it was my freshman year of college, and I had just gotten back home. And okay, by the way, I'll play the video in the background at no volume just so you guys can stay entertained. Just boredom repellent. So for some reason, I had a conversation with my parents about how like, oh, this is one of your last Christmases as a teenager, because I was 18 at the time. And it kind of freaked me out, because I kind of realized like if I want to do anything and still have the fact that I'm like a child impress the audience, I was running out of time. So, and I also had watched some like documentary about special relativity, and I was like, basically, I was lying in bed. I was thinking I should do one thing while I'm still a teenager that maybe seems kind of like, I don't know, cool for a teenager to do. So I thought in my head, like, how does special relativity work? And through a bunch of experimentation, I came up with this. But I didn't have any training in the field, which is why I keep saying things like, oh, I don't know if I'm right, or oh, I don't know if this is like mathematically correct. But what I remember in the okay, I have a notebook out because I just wanted to show you what I remember about like the documentary that I watched was that it didn't really cover the mathematics of how space and time interact, which makes sense because most documentaries are more kind of like pop science, and to get involved with like variables and matrix math, is linear algebra, it's just too much. But I do remember it showed kind of like a two-way graph of time and space, and it kind of hinted at the idea that, like the more general idea that they are two different orthogonal dimensions, and when you're changing your velocity, you're sort of like rotating the space in some way. And so I thought about how, like, if you imagine like the whole idea of like taking on a frame of reference and then accelerating does make simple sense. Because like if you think about opening Google Maps and okay, so I drew this line. So imagine that you're this arrow and this is your car and you're driving along this line and then you reach this point where it curves. So imagine like it's supposed to be pointing right. You would imagine that if you hit this point, the screen would just rotate this way until that this new line was perfectly horizontal, right? Like the goal is like to keep this line horizontal as you're traveling along it, and it would just rotate. And I thought about like, okay, that kind of makes sense, but the rotation has to be different in this space because, okay, this is basically the point of the video, right? If you start with the twin paradox, where you have two twins who start at home planet, and then this is so ugly. Okay, so yeah, basically you have a pair of twins that start at Earth. One of them leaves and comes back, and the other one stays on Earth. And I'm visualizing that by this twin going here, leaving, and then coming back. I thought about like the traditional Google Maps view where it just rotates when you reach the point. And I realized that like in Euclidean space, the twin who leaves and comes back actually travels further. So if you imagine this is like a right isosceles triangle, they end up going square root of 2 times longer. So imagine the twin on Earth ages like 2 years, then I guess numerically the twin that travels will travel 2 square root 2, which is about 2.8 years. And that's actually opposite from what is empirically tested, right? The twin that actually travels ages less. The twin that stays at home ages faster. So I knew that like whatever was happening with Euclidean space, what happened in actual time space-time is probably the reverse somehow. And actually what I'm showing here is kind of like coincidentally relevant. So basically like this thing where like they're both traveling up, which is kind of what happens here. So normally what happens when Blocky travels up is that, okay, so he's going to talk about it in this video. I guess I could turn the volume on.
It shows events happening at the same time, but under the Lorentz transformation, when Blocky starts moving this way, his line of same...
Okay, so before we go to the Lorentz transformation, I just want to talk about like in the normal Google Maps view, I don't know why I keep calling that, when you move up, you rotate in a certain way where you would expect this kind of gray line to turn this way, like this. Because just think about like right angles, right? So as you're kind of turning Blocky's turning counterclockwise this way, counterclockwise, then the line should move like this, right? It should go like this. But I was like, because this is backwards, we need to reverse it. So that's why I thought to myself,
moves this way.
It turns that way, right?
That's because it's all based on the one-to-one diagonal.
And actually, like later, as I thought more about this, I think a simpler way to think about it, instead of this Google Maps backwards thing, is to more think about the diagonal lines of light. Because I think the axiom we're sort of going by is that speed of light is always constant, and we can just assume diagonal lines will always stay diagonal. And a much simpler thing is just scale everything when you need to scale things by those diagonal stretch factors. You can watch the video to sort of understand my thought process there.
Blah blah blah. So for Eraser's second acceleration to be at exactly the same time as Blocky's, he's got to start accelerating here, which appears slightly later for us. The third acceleration is just like the second, but even more extreme. Blocky's line of same time tilts even more, so Eraser waits even longer before accelerating as well. And that just continues until Blocky reaches his maximum speed.
Yeah, that was just me talking about like why when things start to travel really, really fast to an outside observer, they also shorten in distance. But I think that like the what I'm trying to communicate is sort of like this tilting happening in the opposite direction. And I think after kind of thinking about it in my head while I was like lying in bed, I kind of like realized like, oh, this is something that I could code in processing, which is what I did here. The source code is all here, and like the files are all in here as well. Um, and this is the wait, no, that's not the code. That's different. Where's the source code? The source code is here. Um, like it's all extremely simple stuff. Actually, when I did this, I barely knew linear algebra at all. But I think it's how did I do it? Get horizontal line. I'm not quite sure. Um, but one thing I wanted to point out is that like when I run this, do you see this like green grid that's like basically the fabric of space-time? So that's supposed to show the Lorentz transformation, and it's in a pale green color. And one thing that happened at the time was that back in 2015, when I would export videos from Sony Vegas, for some reason they would be transported from one color space to another, and in the process the whole thing would get washed out so that the green lines would appear white, and that would like ruin the visualization because that's such a pivotal part of understanding how this is all working, right? So I guess what I was confused by is like I like WYSIWYG, which stands for what you see is what you get. It's like what you see is what you get, where it's like if you use this color picker and you choose the color like 200, 255, 210, whatever the color was, I don't remember. I want that color to be the exact same code for every time the video is put on a different device or like re-exported. I understand there has to be compression artifacts to make it smaller, like, you know, JPEG compression or MP4 compression. But like if you have a large swath of the screen that is one color and it stays that color, there's no reason that that color can't stay exactly what I picked it as because of things like, you know, this.
By the end of it,
right, like part one for this video is washed out.
right when Leafy and Bubble are born, there is no time distortion whatsoever. Therefore, Bubble ends up the same.
So you can barely see that there's a grid in the background, and that really frustrated me. So anyway, I just wanted to make that video, and also like, I guess in the topic of sort of this intellectual curiosity. So yeah, the last physics class I ever took was high school in 2014, and I think when I saw that people were commenting about how they thought my videos were really well made, I was very honored, but I also felt like I'm not sure what path forward I should go with this. Because when I made this video, I was hoping that it would sort of get traction on the internet the same way that my evolution simulators did, but they didn't, and I'm okay with that because like it just makes sense that like, you know, even 100,000 views I should be really grateful for, and it's just a miracle that the evolution ones got up into millions. But it did make me think, you know, if people really did like the video, like the thing is I'm so used to just putting things on the internet and letting them kind of figure out their spot, but the actual task of sort of like putting it into like educational curriculum, that seems really difficult to me, and I don't even know who to ask for. But also on the topic of like studying physics in school, I've always thought to myself, I really liked the way that they did it back in the lower levels of education, where everyone gets a kind of a sampler of every field. Like, you know, even though that physics isn't my main like expertise, you know, I got a degree in computer science, it's not that I don't want to ever take a physics class again. It would be fun if like every year or every couple years I did another like intro level class so that I could like these sort of videos I could like not be entirely wrong, or like kind of like share with the teachers, but I don't have to fully invest myself to the point where like I'm getting a PhD and my entire life is surrounded with physics, you know? And I think that like every academic subject is like that for me, you know, like with biology or chemistry or history or all these things. I'm like, it would be fun to still be in the loop, but not a full-blown expert. You know, I want to be in the loop. So that's why that's one thing I've been thinking about. And when I watched sort of the 2016 era of my channel, I think to myself, like, I used to dabble with a lot more things. But anyway, thank you for watching this video. How long has it been? It's almost 20 minutes long. Okay. Yeah, thanks for watching this video.
Exactly.
If you want to download this and run it in Processing 4, let me know in the comments. Let me know if you create any interesting visualizations. And you can also tweak it to show new stuff too. And of course, as a disclaimer, it only does flat linear transformations. IOPasta's video talks a lot about like curved distortions, like see how these lines are curved. And, you know, on a local scale, when you zoom into this graph, all, what do you call them, local neighborhoods will look like Minkowski diagrams up close. And that's what
Like this. If it perfectly grazes all the light cones along its way,
it's light.
it's a ray of light.
I'm so smart. No, I watched this video
Meanwhile-
already. Yeah, if you zoom in, it will look like the same way my visualization did, but on a larger scale when you zoom out, these curves, I can never produce that. And I didn't even know that seemed like so impossibly difficult for me at the time. I didn't even like touch that at all. But I just wanted to point that out there that like this video is basically my video, but to the next level, right?
Light cone structure everywhere.
Oh.
All right. Finally, we
So that was a light cone structure everywhere. Okay, yeah, thank you for watching. And yeah, maybe I'll just try to get in contact with more academic people and learn more about how relativity works. And I also, the last thing, I know I've been talking for a while. The last thing I wanted to say is that there are a lot of ways that geometry can work that give you the same result. So I feel like the fact that I thought to myself, what's a way I can do the inverse of Euclidean, like, so like when Euclidean is like this and I did this, you know, like instead of the, yeah, it's like this. And I just randomly picked one. And then that just so happened to be the one that the rest of the physics world has agreed on. I'm just very lucky because I think there have been a lot of other times when I've tried to do a similar thing where I didn't talk to any experts and I tried to like come up with it myself. And then it just came out with a blatantly wrong conclusion or like I remember I tried to prove that all triangles angles add up to 180 in middle school, and in that proof I used that same fact, that like the fact that all angles add up to 180 in the proof, which makes it circular reasoning, so it's invalid. And I was really embarrassed when my math teacher called me out on that. So I guess my point is that like I think I just got very lucky that it's the same mathematical model, because like I can just easily imagine there's all different ways of distorting like the Cartesian grid that give you the same result but have very different results when put under a lot of other types of transformations. So I just feel very lucky. But I think that like what confirmed it in my head that I was probably on the right track was that the equation derivation process near the end here. So where I try to figure out like the value of this equation right here, I did it by like using my like linear transformation thing and then like doing geometry to it, and it gave me the same result, which still isn't proof that is correct, but it's just another like hint in the right direction. So I don't know, I just feel very lucky because, you know, usually as a beginner or as a college freshman who hasn't taken any classes in this, you just get things wrong. And I don't know why I was so like confident to just throw that out on the internet, but it's not the first time I've done that. Anyway, thank you for watching. Bye.